Hello, everyone. My name is Dennis Burrell. I'm a product manager at Ventev, and we're going to go over some information today that I think will be very enlightening and beneficial to you. So let's just get started. Our agenda for today is we'll give a brief overview of Ventev, followed by a section called All Antennas Are Not Created Equal, where we'll go through some antennas and how Ventev goes about doing their antenna designs and setting their specifications. And then we'll discuss some antenna innovations as far as the design, development, and testing of some of our newer products. Then we'll have Jim Baker come on and talk from a power perspective. I've got the power, taking your telecom closet outdoors, design, development, and testing. So who is Ventev? Ventev is an industry leader in third-party antennas, enclosures, and power systems, and wireless ecosystem accessories. We like to call ourselves the ecosystem provider. We don't do any active radios or anything. We just do the ecosystem around the radio. So by the ecosystem, we're talking antennas, enclosures, cables, and power solutions. Our products improve the performance, the ease of installation, and enhance the aesthetics of wireless networks. We're very big on aesthetics and small form factor. So that's a big trend right now with a lot of the companies. They want Wi-Fi, but they don't want to see it. They want it hidden. And we have a ton of solutions to make aesthetically pleasing and hidden Wi-Fi solutions. We're authorized ecosystem development partner for Cisco, Aerohive, Fortinet, Samsung, and most major Wi-Fi access point manufacturers. And we also work closely with channel partners to deliver increased value and end user Wi-Fi deployments. As you can see down the bottom, those are some of the manufacturers that we work with. Highlighting quickly, you see two Cisco logos there. One is that we're a preferred solution partner for Cisco for Wi-Fi, and recently we became a partner for IoT solutions for Cisco as well with their build-in program. And then with Ragent, we're doing a lot of things with Ragent for industrialized solutions as well. So what problems does Ventev solve? Coverage, capacity, aesthetics, solution, security, protection, and power. Those are our main tenets that we try to drive in everything that we do. And how do we solve these problems? I mentioned earlier that we're an ecosystem provider. And for some of you that may not know, Ventev was known as TerraWave, so you may be more familiar with the TerraWave name than the Ventev name. The Ventev name was a branding decision, but all of our antennas, which were TerraWave antennas, we still are branded as a TerraWave antenna by Ventev. So just to give you guys an idea of Ventev and the relationship with TerraWave. And then we're owned by Tesco. So Tesco is a Wi-Fi manufacturer, over 30,000 products, 350 companies that they represent. So we're their branded manufacturer. I mentioned earlier, we do antennas, indoor-outdoor enclosures, standard and custom mounts, integrated wireless power systems, and also bulk cable and quick turn cable assemblies. So who do we solve problems for? So we pretty much play in all verticals that you can think of: large public venues, healthcare, higher ed, industrial, manufacturing, as well as utilities. So at Ventev, we're very stringent on our design methodologies when it comes to antennas. We like to say that we're performance and quality based, and they are key metrics in our antenna designs. We want to provide an antenna that performs up to specification, as well as a quality antenna, so you have no concerns about using it in the different environments that you may need an antenna for. Most of our designs, the foundation for them are dipoles. And the reason why is dipoles gives a natural 60-degree E-plane beam width. And then we take it from there as far as the design on how to either broaden or lessen that pattern in the E-plane and then also the H-plane by doing some things that we've learned along the way as far as designing and analyzing antennas. So then analysis, test, repeat. We use numerical analysis for our design and optimization of our antenna designs. Then parameter testing, gain, beam width, viswar, et cetera. All of your standard specifications that you'll see on spec sheets as far as how to read what the performance of the antenna is from those perspectives. And then we fine-tune analysis. We use fine-tune analysis until we get our desired test results. So in between that parameter testing and that fine-tuning, parameter testing is we're going to a chamber to test performance, right? And once we get that performance, we take it back and we verify if it's meeting specification. If not, that's where the repeat comes in. So it's cyclical till we get to the point where we think we have a product that we want to bring to market. So what I wanted to go over with you guys is our warehouse antenna design example. We're seeing a lot of interest in warehousing in that vertical, and we had some products already existing, but we needed a product that would cover an entire aisle of a warehouse. And just the aisle and no overspill into the following aisle, but from a length and width perspective. So we wanted to come up with an antenna that had at least 115 degrees of horizontal beam width. So what you see to the right is actually a picture of the antenna, the numerical analysis picture of the antenna. And I'll just go through how we went about coming up with that design. So we started out with printed dipoles for the design. Then the height of the dipoles is much lower than a quarter wavelength to widen the horizontal beam. As I mentioned earlier, we started with 60 degrees. So by lowering those dipoles height, we can broaden that beam width, and that's what we wanted to do here. The low band and high band arrays use separate reflectors so that they won't interact with each other. The high band arrays are located toward the edge of the antenna, and the high band reflectors are higher than the low band reflectors to present shadowing from the low band arrays. And by shadowing, we mean that it wouldn't interfere with that pattern so that we could get the true pattern that we were looking for. And to minimize the shadowing among the low band radiators, adjacent arrays are offset in elevation from each other. So you'll see the different heights within the array for each of the dipoles representing the port of the antenna. This is a 4-port antenna design. And then finally, we use CST to optimize the radome shape and spacing among the arrays to obtain a stable patterns and broad beams at both low and high bands. So this ended up being a radome that has pretty much a curved look, aesthetically pleasing curved look, where it's in the center, it's a little higher, and then it curves lower towards the edges of the antenna. So right here, this just shows some of the numerical analysis for the antenna. This is at 2.45 gigahertz. And as you can see, we had no problem meeting the vertical beam width, which was 11 degrees, but the hard part was the horizontal beam width, right? So this is what we're concentrating on the show here at 2.45. And as you can see, we're at around 117 degrees in assimilation. And then down at the bottom in the center, that's the actual measurement of the antenna in the anechoic chamber. So as you can see, pretty close match to what we're seeing in our numerical analysis simulation for the antenna in the low band.
Hey, Dennis, I have a little quick question.
Yes.
One, what's the software you're running on this, and about how long did it take to do this simulation? I mean,
That's a great question. So
something you whipped out in an afternoon, or it took a lot of time?
it takes, well, so it depends on the type of computer you have and the type of and the amount of memory that you have in the computer as well, because these are pretty intensive runs, simulation runs. So they can take on the order of hours depending on how many meshes that you use on the antenna. So you mesh the antenna into little squares, and then you process it. So depending on how you mesh the antenna in the simulation, that takes up the time. And then it also it depends on the type of card that you're using, like the NVIDIA card or whatever card you're using, what kind of strength, firepower that card has. So this is the 5 gigahertz band, the upper band. As you can see in the design, there's a little bit of ripple on the 5 gig band, but it doesn't have ripples that are deep enough to affect the beam width. And by beam width, I'm talking about the 3 dB beam width, and that's the peak of the antenna where it falls off on either side of the chart that you're looking at, 3 dB. So that's how we calculate or we specify the beam width of the antenna. This was a cut taken at 5.7 gigahertz. And for this one, we are at, and excuse me, I'm moving, didn't mean to do that, but we're over 115 degrees. So this is the actual antenna. We put the VEX files in Ekahau, and we had one of our customers do a predictive in Ekahau for the antenna. They used a Cisco 9130 AXE, their newest access point. The antenna is 35 feet high. It's a 5 gigahertz only design. Power level was set as 14 dBm. The shelves are 20 feet high, 20 feet high still with 27 dBm of loss. And the aisles are 350 feet long by 15 feet wide, except for the wider ones in the middle, those two, which are 36 feet. And as you can see, with one antenna, we can cover an aisle that's 350 feet long. So this predictive is of another warehouse that the customer is doing as well. This one has more aisles, slightly different widths of the aisles in some aspects, using the same parameters as the earlier one. But in this one, they did 2 antennas per aisle because these aisles are 370 feet long. And with one antenna, we were right on the edge at the 350. So to ensure that they have full coverage, they ended up putting in two of the warehouse antennas per aisle to get the coverage. So now I want to go and discuss our small form factor antennas. And as you know, as I mentioned earlier, we are very high on aesthetics and pushing the envelope for size of the antennas or size of our antennas. So this is a 6 dBi antenna. Our original patch antenna was approximately 9 by 9 inches, as you can see from the purple square to the right. So in going through our designs and trying to come up with smaller form factor antennas, we go through some different designs on how we can minimize the size of the antenna, but still achieve the same gain and close to the beam widths as possible. So our first design that we came up with was our micro patch antenna. And we did this design probably about 4 or 5 years ago. And this design is the yellow or the gold square outline. And that was a 4.7 by 4.7. So we were able to almost reduce this size and cut it in half, but still keep the same performance. And all of this is because of the numerical analysis tools that we use and the process that we go through. Chief, you had mentioned earlier, you was asking about the time that it takes. We like to go through iterations until we get it right. So if we don't get it right on the first pass, we'll do a second pass and even a third pass. One of the things I can say about the warehouse antenna, a lot of the customers was asking about that warehouse antenna, and it took us almost a year to bring that to market because we wanted to make sure that we didn't cut corners and that we were achieving what we said we would be able to achieve as far as the that horizontal beam width. That was the main component of that antenna that we definitely wanted to make sure that we were able to achieve. So we went through a lot of iterations on that antenna, and we just wanted to make sure that that was a quality product that we brought to the marketplace.
Dennis, we had a quick question from Twitter. I was wondering if I could jump in with. Steve Rodriguez wants to know what RSSI was being predicted at the end of that 350-foot aisle.
They were, I think it was -67. I'm not sure. I could find out, but I'm thinking that's what they designed for, because these will be handheld devices, 5 gig only handheld devices, so it won't be a high data rate going through them in the warehouse.
All right, thank you very much.
Mm-hmm. So then our next antenna that we came out with was our nano patch design, and that was a 4x4 inch antenna. So trying to push the envelope on the design, making them smaller, aesthetically pleasing, so that we have something that's somewhat of a differentiator for us in the marketplace as a third-party antenna provider. And then we came up with the Pico Patch, 3.7 inch diameter. We wanted to come up with a form factor that was slightly different than the square. So that's how we came up with the Pico Patch design. Now the Pico Patch designs are 5 gig only designs. So we were able to make those smaller, but the caveat is that they're only 5 gig only. Now each of these antennas are 4-port antenna designs. So they're 4 ports on each antenna. The first 3 dual band, dual polarized ports, and then the 2 Pico patches that you see here are single band 5 gigahertz designs, 4 ports. And then finally the Pico Patch 2, that is about the size of a business card. 5 gig only design, the size of a business card. And we was actually able to get almost around 7 dBi gain out of this antenna. So we've had a lot of good response for that, for some of the Fortune 100 companies using that in some of their deployments where aesthetics were really key, and they had a 5 gig only design and they didn't want to see the antenna, or they wanted it minimized as much as possible. So our newest design is our Femto Patch. So how do we come up with our Femto Patch? The Femto Patch is a dual band dipole antenna design. It's dual polarized. We optimized this one in HFSS using return loss, isolation, and the gain pattern to keep the efficiency as high as possible. And then we used a single PCB with connector placement and routing for efficient, to make it efficient for space savings. So one of the things that we do with our antennas when we design them, if it's a 6 dBi antenna, we don't specify that 6 dBi actually coming out of the radiator. We specify our gain out of the cabling of the antenna, so right at the connector. And the majority of our antennas have 3-foot pigtails on them. So the loss of RG58 cable, which we have, is 1 dB at 2.4 and around 2 dB at 5 gig. So in order to get a 6 dBi antenna, we designed the radiators to be 7 and 8 dBi respectively, so that at that connector, if you were to measure the gain, it's as close to 6 dBi as possible. And then we have losses in the FR4 PCB that we have to take into account as well by playing with the transmission line to increase or decrease its length to get us around that 6 dBi. Now, I don't know if you're familiar with FR4 FR4 material, but FR4 material is one of the more standard or readily available materials out in the marketplace. But one of the drawbacks for FR4 is the batch-to-batch consistency, depending on how it's manufactured. So one set of antennas you could bring in could be, say, 6 dBi. Another set of antennas you could bring in could be maybe 5.5 or something, depending if the consistency of the PCB material isn't the same. But we were lucky enough to find a PCB manufacturer of FR4 that keeps their PCB consistent. It's been consistent over the last 8 years, so we don't have that variation in the material that we use for FR4. So we are able to keep a consistent number as far as our gain over batch to batch over the thousands of antennas of these designs that we've released to the marketplace. So this is a picture of our Femto Patch. Gain is 6 dBi, visual is less than or equal to 2. Our H-plane beam width is 80 and 120 degrees. The first beam width is 2.4 and the second is 5 gig. Then the vertical beam width 80 and 50. Front to back ratio, that's the difference between the peak on the front and the radiation coming off the back of the antenna. 9 dBi on 2.4 and 15 dBi at 5 gig. And as you can see for the dimensions, it's 3.4 by 3.4. So we were actually able to get a dual band design approximately the same or a little slightly less than our Pico Patch design. So we were very proud of this design. As you can see from the picture, this antenna right here, this picture, this sample of the antenna right here has a dart connector on it. We're part of Cisco's ADP, their development program. So they gave us access to the dart connector. So we have the ability to come out with DART-enabled antennas now. So just a little caveat for you guys, if you're looking for DART-enabled antennas or DART jumpers, we have the capability to produce and sell those now.